All right, so we are about to start Chapter 9. Chapter 9 is all about work and kinetic energy. And to start off with, we're going to start by looking at what's called the scalar product. So just as a little reminder, if I have a vector, let's just call this vector A. We kind of saw this a little bit when we were looking at Chapter 3 with vectors. If I were to multiply vector A by a scalar. So one, keep in mind, a scalar is any physical quantity like volume or mass or time that's only described by a magnitude, a number in units. And remember, a vector is anything that also needs a direction. Things like acceleration, velocity, position, displacement. So if I have a vector quantity, and let's say I multiply it by a scalar. So if I did 3 times vector A, whoops. If I did 3 times vector A, that's just going to be the same direction as vector A, but 3 times as long. So if A, pointed to the right, and let's say A was a force vector of 10 newtons, 3 times A would just be the same direction as A, but 3 times as long. If I had a, let's say, vector B, again, this could be a force vector, it could be a displacement, something like that. But let's say I multiplied vector B by a scalar which was negative. So like -2 times vector B. Again, this is going to double the length of it, but since it's negative, it's going to be a vector in the opposite direction. So again, if I just had vector A, let's do this over here, bam. I want to draw, let's do red. So vector A, right here, if I multiply it by a positive scalar, like 3, then 3 times A is going to have the same direction as A, but 3 times as long. Or if I have, let's say, vector B, again, it could be a force vector, displacement, whatever. If I multiply it by a negative number, like -2, keep in mind the negative of a vector, same length, opposite direction. But in this case, if I multiply it by -2, then it's going to have twice the length it did before, but exact opposite direction. Okay, so that's multiplying a vector by a scalar. What you're going to look at now is what's called the scalar product. Scalar product or dot product. So scalar product, as the name implies, the end result is going to be a scalar, just a number and units. In chapter 12, we're going to look at what happens if I do what's called a cross product. And in that case, the end result is going to be a vector. So if I have 2 vectors, A and B, the dot product of those 2 vectors is defined as the magnitude of the first vector times the magnitude of the second vector times the cosine of the angle between the two. So for example, let's say vector A has a length of, we'll just call it 10 meters. Vector B, let's just say, has a length of 5 meters. Now let's make it 6 meters. And let's say the angle between the 2 vectors was 35 degrees. Just by the definition of the dot product, it's the magnitude of one vector times the magnitude of the second vector times the cosine of the angle between them. So for this particular case, A dot B is equal to the magnitude of A, which is 10 meters, times the magnitude of B, which is 6 meters, times the cosine of the angle between them, which in this case is 35 degrees. Break out my calculator here. We've got 10 times 6 times cosine of 35. What you end up getting is 49.1. meters squared. The units of the dot product is always the product of the two units of each vector. So in this case, it's just two displacement vectors. The units would just be meters squared. So why is this going to come up? Let me move this down some. Well, what we're going to see in this chapter is that work. So a little preview. Why are we doing this? Work, which hopefully you remember from your physics course, Physics 11 or high school physics. Anytime you exert a force on an object and that object moves through a displacement, you do work on the object. And what we're going to see is anytime you do work on an object, you are transferring energy either to the object or from the object. So a little preview, the reason we're going to care about all this is because work ends up being the dot product of the force on an object times the displacement over which the object travels while that force is being acted upon it. So, a little preview, that's why we care about the scalar product. So, conceptually, oops, let me just move this down. Bear with me. Okay, so what is the dot product conceptually? Well, again, let's just choose two random vectors. Let's say vector A. Whoa, what happened there? So vector A, let's say points to the right. And vector B, again, let's say it's up at some angle. And here's the angle between them. Well, if you look, let me switch colors here. This little piece right here is equal to B times the cosine of the angle. So what is A dot B conceptually? Conceptually, A dot B is the magnitude of vector A times how much of vector B points in the direction of vector A. So that's what it is conceptually. It's the magnitude of the first vector times how much of the second vector points along the direction of the first vector. So in this case, again, going over here, the dot product of A dot B is going to be the magnitude of vector A times how much of vector B points along the direction of A. So a couple things about the dot product, and let's actually look down here. Whether or not the dot product is positive, negative, or zero only depends upon the angle between the two vectors. And this angle here, so when using A dot B, the dot product of vectors A and B, the magnitude of A times the magnitude of B times the cosine of the angle between them. One important thing is this angle is always going to be between 0 and 180 degrees. You choose the smaller of the two vectors. So for example, like right here, if I'm looking, this angle, maybe it looks like it's about 30 degrees. But you could also say, well, the angle between them is 330 degrees. You're looking at the smaller angle between 0 and 180. What this means is that whether or not the dot product is positive, negative, or zero only depends upon the angle between the two vectors. So here, if the angle between the two vectors is zero, so they point in the same direction, the dot product, you're just multiplying the two magnitudes together because cosine of 0 equals 1. If the angle is between 0 and 90, so if the angle between the two is between 0 and 90, that means the dot product of A dot B, which will be AB times the cosine of the angle between them, that's going to be greater than 0. If the angle between the two vectors is 90 degrees, cosine of 90 degrees is 0, which means the dot product is 0, which also makes sense because if they are perpendicular, there is no component of B that's along the direction of A. If the angle is between 0 and, if the angle is between 90 and 180, then in this case, if our angle is greater than 90 and then less than or equal to 180, cosine of that is negative, so our dot product is going to be negative. And in the case when it's exactly 180, cosine of 180 is -1, so the dot product is just negative the magnitude of A times B. So summarizing all of that in terms of just the angles. So for the dot product of two vectors, again, A dot B, it's the magnitude of the first vector times the magnitude of the second vector. Whoa, I don't know what happened there. Times the cosine of the angle between them. So let's just look at our possibilities. If the angle is between 0 and 90 degrees, the dot product of A dot B is going to be greater than 0. If the angle between the two vectors is 90 degrees, then our dot product is going to equal 0. And then if our angle is between 90, oops, what was that? That was less than, greater than, or if the angle is greater than 90 or less than or equal to 180, then our dot product is going to be negative. Okay, let's grab a new page. So if you've taken math, I think they do it in math 5B, then one of the things you're going to see is if I express a vector as the x component in the I direction plus the y component in the j direction plus the z component in the k direction. And b, second vector, is bxi plus byj plus bzk. Another way of expressing the dot product is it's equal to the x components of each vector multiplied together plus the y component of each vector multiplied together plus the z component of each vector multiplied together. These give you the exact same answers. First, I'm going to show you that they give you the exact same answers, and then I'm going to show you how that comes about and why you get this. So let's say vector A, again, we're just going to call it a displacement vector. Let's say that this is 10 meters to the right. And vector B, we'll say is another displacement vector. And let's just say it's 9 meters. And this angle here is, we'll call it 30 degrees. So the first way of calculating the dot product is the dot product of A dot B. Again, it's the magnitude of A times the magnitude of B times the cosine of the angle between the two vectors. So for this particular example, the magnitude of A is 10 meters. The magnitude of B is 9 meters. And the angle is 30 degrees. if I take 10 meters times 9 meters times cosine of 30 degrees, what I get is 77.9, and in this case the units would be meters squared. Now let's look at this using IJK notation. So vector A, in this case it's just going to be 10 meters in the I direction. There is no Y component. Vector B, in this case, the X component of B points to the right, it's positive. The angle is 30 degrees. The X component is our adjacent side. So what we're going to have is B is 9 meters times cosine of 30 degrees in the I direction plus 9 meters times the sine of 30 degrees in the J direction. Working this out, let's see what we get for B. So I have 9 times cosine of 30. So we get 7.79 meters as the X component of B, plus 9 times sine of 30, 4.5 meters in the J direction. So now let's look at getting A dot B by using AX BX plus AY BY plus AZ BZ. So X component of A is 10 meters. X component of B, 7.79 meters, plus the Y component of A is 0. The Y component of B is 4.5 meters. What you end up getting is 77.9 meters squared. It doesn't matter if you use dot product of two vectors. If you have the X and Y and Z components, it's just AX BX plus AY BY plus AZ BZ. AZ BZ. If instead you have the magnitudes of the vectors and the angle between them, then you can use the magnitude of A times the magnitude of B times the cosine of the angle between them. Why does this work out the same? Well, let's look at unit vectors. Remember, our unit vectors are, oh, got to change it back. Try and wrap this up soon so it's not too long. Unit vectors are, remember, I is a unit vector pointing in the X direction. J, unit vector pointing in the Y direction. K is a unit vector pointing in the Z direction. And remember, the magnitude of any unit vector is 1 by definition, right? A unit vector points along an axis, has a length of 1, and has no units. Other thing to keep in mind is, 1, if I take the dot product of any two vectors, any two unit vectors dotted with itself. So I dot I, or J dot J, or K dot K. It's the magnitude of the first vector, which is 1, times the magnitude of the second vector, which is 1, times the cosine of the angle between them. Angle between a vector and itself, whoops, is 0. So what you get is any unit vector dotted with itself is going to just give me 1. So I dot I is 1, J dot J is 1, K dot K is 1. Now any unit vector dotted with a different unit vector. So I dot J or J dot I or I dot K or K dot I or K dot J or J dot K. These all give values of 0. What is that? I have no idea what that is. Okay, so I dot J, J dot I I dot k, k dot I, k dot j, j dot k is 0. Why? Well, remember the dot product is the magnitude of one vector times the magnitude of the second vector times the cosine of the angle between them. So the magnitudes of any dot product or any unit vector is 1. So I take 1 times 1. The angle between any two unit vectors is 90 degrees, which means that any unit vector dotted with another unit vector, the end result is 0. So putting that all together, let's look at where this dot product of ax bx times ay by plus az bz comes from. So this will be the end for dot product. Let's say a equals axi plus ayj plus azk. And b is bxi plus byj plus bzk. Now if I do a dot b, what I'm really doing is, for something like this, taking ax I and then dotting it into all three of these for b, taking ayj, dotting it into all three of these, azk, dotting it into all three. So the end result is we're going to have 9 different terms. Of those 9 terms, only 3 are going to survive. So I have axi times all 3 of these. So I get ax bx times I dot I plus ax by I dot j plus ax bz I dot k. So that was from taking axi and dotting it into all 3 components of b. And then I also have plus plus ay bx times j dot I plus ay by times j dot j plus ay bz times j dot k. That comes from taking ay and dotting it into all 3 components of b. And then finally, last set is I take azk and dot it into all 3 components of b. So az bx times k dot I plus az by times k dot j plus az bz times k dot k. So we've got 9 different terms. And keeping in mind that any unit vector dotted with itself is 1, and any unit vector dotted into another unit vector, and so on, is 0. Which means that out of these 9 terms, only 3 are going to survive. So I dot j is 0, I dot k is 0, j dot I is 0, j dot k is 0, k dot I is 0, k dot j is 0. The only terms that survive are ax bx I dot I plus ay by j dot j plus az bz k dot k. And since I dot I is just 1, j dot j is just 1, k dot k is just 1, the end result is if I have x and y components of the 2 vectors a and b, the dot product can be written as ax bx plus ay by plus az bz. And that's it. That is the dot product. And again, the reason we care is because work is defined as the dot product of the force dotted with the displacement. So I'm going to stop this. We'll do one quick little example problem, and that'll be it for scalar product. And then on Thursday, we're going to jump into Chapter 9, Work and Kinetic Energy. All right. Hope that wasn't too long. And yeah, hopefully I'm going to start using Zoom, but we'll see. We're not allowed to go into campus yet. Stay tuned.